नमस्ते दोस्तों। आज हम एप्पल के वैज्ञानिकों द्वारा तैयार की गई एक जबरदस्त रिपोर्ट पर चर्चा करने जा रहे हैं। जी हाँ, वही आईफोन वाला टेक दिग्गज एप्पल। यह रिपोर्ट चैट जीपीटी, डीप सीक, गूगल जेमिनाई जैसे लार्ज रीजनिंग मॉडल्स LRMs पर केंद्रित है और इसका नाम है द इल्यूजन ऑफ थिंकिंग, सोचने का भ्रम। जैसा कि नाम से ही पता चलता है, हम इस रिपोर्ट के जरिए यह समझने की कोशिश करेंगे कि क्या हमारे AI चैटबॉट सचमुच सोच सकते हैं या फिर वे केवल अपनी विशाल लर्निंग लाइब्रेरी से जानकारी को मिलाकर परिणाम दिखा रहे हैं। आइए समझते हैं।
Our guide for this journey is a really fascinating research paper from Apple. It's titled, pretty aptly, I think, The Illusion of Thinking, Understanding the Strengths and Limitations of Reasoning Models via the Lens of Problem Complexity. It's a true deep dive into how these AIs reason, or, well, as we're going to find out, sometimes how they don't quite manage it. So our mission today is pretty clear. We want to unpack what these powerful large reasoning models, or LRMs, can actually do. What happens when the problems get too tough for them? And importantly, what does all this mean for the future of AI and for, us trying to understand it all? Think of this as your shortcut to really grasping the inner workings, the sort of digital brains of these incredibly sophisticated AIs.
It's pretty remarkable, isn't it? Because we're constantly hearing about AI doing these incredible things, generating amazing art, writing complex code. It almost feels like magic sometimes. But what makes this Apple study so compelling, I think, is that it doesn't just show us what AI can do. It actually takes us inside their problem-solving process. It's kind of like getting a peek behind the curtain, into their thought process, if that's even the right term, to see not just if they get the right answer, but how they try to get there, and maybe even more important, where they stumble and why they stumble. And the way they do this is by watching how these AIs tackle problems that get progressively harder in a very controlled way. Imagine a student learning math, right? You start with simple addition, maybe 2 plus 2. Then you move on to multi-step equations, then maybe complex algebra or geometry proofs that need a whole sequence of logical steps. This study basically maps out the AI's journey through these escalating challenges. And the insights that they got are, well, they're pretty profound. It forces us to ask, is this AI truly thinking in a way we understand it? Or is it doing something else entirely, something that just looks like thinking? And what can we learn about intelligence itself, both human and artificial, from watching this?
Okay, right. Let's try and unpack this a bit. Before we get into the really surprising findings from the paper, maybe we should quickly lay the groundwork. What are we actually talking about with these AI models? You've almost certainly heard of LLMs, right?
Mm-hmm.
Large language models. Yeah, these are basically super smart language machines. Imagine a gigantic digital library. But instead of just storing books, it's read and really processed almost everything written on the internet. Books, articles, blogs, conversations, just a staggering amount of text. And because it's seen all this language, it learns the patterns, how words connect, how ideas flow. And that lets them understand what you're asking, generate text that sounds incredibly human, write stories, summarize long documents, even translate languages pretty fluently. Think about the autocorrect on your phone, how it predicts the next word. It's like that, but on an unbelievably massive intelligence scale. It's always predicting the next most likely word or phrase to create responses that are coherent, relevant, and, grammatically correct. They're amazing at generating text that sounds really smart, but sounding smart. Well, that's not always the same as actually being smart, is it?
Exactly. That's the crucial point. LLMs they've totally changed how we interact with tech. They're masters of language, understanding context, generating fluent, creative text. They've nailed linguistic performance. But the next big step, the real frontier, and this is what the Apple paper digs into so well, is whether these models can genuinely reason. Can they go beyond just sounding intelligent? Can they actually be intelligent in a way that involves structured step-by-step logic, real problem solving, maybe even correcting their own mistakes? And that's where this idea of LRMs, large reasoning models, comes into the picture.
Right, LRMs, large reasoning models. So these are kind of the next generation, a more specialized type of LLM. And the key difference, the thing that makes them so interesting for AI research, is that they're specifically designed to, show their work, to display their thinking process before they give you the final answer. It's exactly like that tough math teacher you might remember. The one who didn't just want the answer to a complex problem. They insisted, show your steps. I need to see how you got there. That's basically what LRMs are trying to do. They generate something the researchers call a chain of thought, or COT for short. And it's essentially a detailed step-by-step reasoning process laid out for us to see. And this chain of thought, it's not just random words. It's the AI trying to articulate what look like its internal logical steps. It might show calculations, outline different possibilities, or even try to correct its own earlier mistakes. Sometimes it even explicitly tries to double-check its work. Just like how you or I might reread something we wrote or redo a calculation to catch an error. The paper actually mentions that these models might literally output things like thinking. Okay, wait, let me double-check this step. Think right in the middle of their process. It really feels like you're getting this privileged glimpse into their digital mental space, like an internal monologue guiding them towards the solution. And the paper looked at some really cutting-edge examples of these LRMs models you might have heard of, like OpenAI's O1 or O3, DeepSeek R1, Claude 3.7 Sonnet Thinking, Gemini Thinking. These are the big players. The core idea, the hope really, was that this explicit step-by-step thinking process, this chain of thought, would make them much better at tackling really complex problems. The kinds of problems that need more than just recognizing patterns, problems that genuinely demand logical deduction, planning, and working through steps.
It's a powerful idea, isn't it? A powerful hypothesis. The belief behind LRMs was that by generating these transparent, explicit steps, they could effectively break down really complex problems, turn them into smaller, more manageable subproblems. And this approach, at least in theory, should let them handle challenges that absolutely require a sequence of logical operations. It shifts the focus. It's not just about finding the answer anymore, but about understanding and actually constructing the path to that answer, which, intuitively feels much closer to how human intelligence often works, doesn't it? But this immediately brings up a really critical question, one we should probably keep in the back of our minds throughout this whole deep dive today. Is this thinking that we're seeing, is it genuine intelligence? Or is it a remarkably sophisticated, maybe even elaborate form of pattern matching that just mimics reasoning incredibly well? Think about how you solve a puzzle, like a jigsaw or Sudoku. You don't just magically know the answer. You try things out, right? You test possibilities, you make mistakes, you backtrack, you correct yourself based on what works and what doesn't. LRMs are trying to emulate that iterative self-correcting process. And that's exactly why studying their thoughts so carefully, seeing where they nail it, where they mess up, and why is so incredibly insightful. It helps us understand the current state of AI, its capabilities, but also its fundamental limitations. It helps us try to separate the illusion of thought from, well, maybe something closer to genuine cognition.
Okay, so if you really want to test if an AI is genuinely thinking and reasoning, or if it's just, pulling answers from its memory, how do you actually do that? Traditionally, AIs were tested on standard benchmarks, things like complex math problems, coding challenges, general knowledge quizzes, that sort of thing. And for a long time, these models got amazing scores on these tests, which led a lot of people to think, wow, they're really reasoning, almost like humans. But this Apple study, well, it found some pretty significant problems with those traditional testing methods, foundational issues, really. One huge limitation they pointed out is something called data contamination. Cotto. Right, imagine you're a student preparing for a big exam. If you somehow saw the exact answer key beforehand, maybe because those same questions were used in lots of practice tests, you might ace the exam, right? Get a perfect score. But did you really understand the material? Or did you just recall the memorized answers? That's the potential issue with AI testing. These large models have been trained on unbelievable amounts of data, basically, the whole internet. So it's very likely they've already seen problems very similar, or maybe even the exact solutions, to those traditional benchmark questions during their training. So when they solve them, it might not be genuine reasoning at all. It could just be recalling or blending memorized patterns, like acing a test because you recognize the questions, not because you actually worked out the answers from scratch. And the other big problem with those older tests is that they usually only cared about the final answer. Was it right or wrong? That's it. They give you almost no insight into the AI's actual thought process. How did it get to that answer? It's like a math teacher who only looks at the very last line of your solution for a complex, multi-step problem. They don't check your working at all. You wouldn't know if the student truly understood the method, or if they just, I don't know, copied the final answer from a friend. This lack of transparency hides potential flaws in the AI's reasoning. It makes it really hard to understand why it got something right, or maybe even why it got something wrong.
Exactly. And this is where the researchers behind this paper got really clever to get around these big limitations, the contamination, the lack of insight. They came up with a brilliant approach. They use special puzzle environments. Think of these like custom-built AI playgrounds, meticulously designed specifically to isolate and test true reasoning ability. And the genius of using puzzles is that they allow for what the paper calls fine-grained control over complexity, which means the researchers could make the puzzles just a little bit harder or a little bit easier in a very precise, measurable way, often just by adding one more element, one more disk, one more checker, without changing the basic rules of the game. It's like having a puzzle where you can add just one extra piece at a time. It lets you really dial up the difficulty very, very precisely, or adding just one more variable to an equation, subtly making it harder. And here's the really crucial part. These puzzles were designed to be completely new to the AI. This way, they could be sure the AI hadn't just memorized the solutions from its training data. It was forced to reason, to apply the rules logically from first principles. These puzzle environments put the emphasis squarely on algorithmic reasoning. The AI had to follow precise, step-by-step rules, almost like following a complicated recipe. And because these are puzzles with very clear rules and very clear steps to check, the researchers could literally scrutinize every single move the AI made, every single line in its chain of thought. This gave them an incredibly detailed picture of where it went wrong, if it did, and why. It's like giving the AI a surprise pop quiz on material it's definitely never seen before, and then recording every single thought, every hesitation, every mistake it makes along the way.
And these weren't just random puzzles either. They picked some real classics, logical challenges that people have used for, well, decades to test human intelligence and problem-solving skills. The paper focuses on 4 main types that turned out to be particularly revealing. First up, there's the iconic Tower of Hanoi. You've probably seen it. Imagine 3 pegs and a stack of different sized rings on one peg. The biggest on the bottom, smallest on top. The goal is simple. Move the entire stack to another peg. But there are 2 strict rules. 1, you can only move 1 ring at a time. 2, you can never place a bigger ring on top of the smaller one. The amazing thing here is how quickly it gets difficult. If you have n disks, it takes 2 to the power of n minus 1 moves. That's the minimum. So for just 3 disks, it's 7 moves. Okay, manageable. But for 10 disks, that jumps to 1,023 moves.
Yeah.
It forces really deep multi-step planning.
Right. Then they used the checker jumping puzzle. Picture this. You have a line of, say, red checkers on one side, an empty space in the middle, and blue checkers on the other side. Maybe like R, R, B. The goal is to completely swap their positions. All the blues end up where the reds were, and vice versa. The rule seems simple. You can slide a checker into an empty spot next to it, or you can jump over one checker of the opposite color to land in an empty space. But here's the kicker. No moving backward. And if you have n checkers of each color, the minimum number of moves is n plus 1 squared minus 1. So for just 2 red and 2 blue, like the example, that's 2 plus 1 squared minus 1, which is 8 moves. This puzzle is great for testing an AI's ability to plan ahead and see the consequences of its moves, because one wrong step, one backward move, and you can easily get stuck.
Next, they use the classic river crossing puzzle. This is like those brain teasers you hear about. You know, a farmer needs to get a fox, a chicken, and a bag of grain across a river in a tiny boat that can only hold him plus 1 item. Or maybe more complex versions with missionaries and cannibals. The challenge always comes down to strict safety rules. Like you can't leave the fox alone with the chicken, or the chicken alone with the grain, or in the missionary version, the cannibals can never outnumber the missionaries on either riverbank or else, well, you know. The difficulty shoots up with more characters and more complex rules. It requires really careful sequencing and foresight to avoid breaking the rules. It really tests the AI's ability to juggle multiple constraints at the same time, not just follow a straight path.
And the last one they highlighted was Blocks World. Imagine a table with several stacks of blocks, each labeled with a letter. Your goal is to rearrange these blocks into a very specific target configuration, maybe stacking them to spell a word or creating a specific tower shape. The rules are pretty straightforward. You can only move the top block from any stack, and you can only place it either on an empty space on the table or directly on top of another block. What makes this tricky for an AI is that you often have to move blocks out of the way temporarily just to get to the one you actually need. Then you might have to move them back later. It demands real foresight, planning intermediate goals, kind of like how a person might think several moves ahead in a game like chess. You have to clear obstacles to achieve your main goal. So these 4 puzzle types were really ideal for this study. Why? Because they allowed the researchers to check literally every single step, every single thought the AI generated. This gave them this incredibly fine-grained picture. Where did the AI succeed? Where did it fail? And crucially, why did it fail at that specific point? It's like putting the AI into this hyper-controlled learning lab where every single action, every decision can be put under a microscope and analyzed. Just like how we learn, right? By trying things, by making mistakes, and then hopefully reflecting on those mistakes. These puzzles create a precise environment for studying the AI's problem-solving process, revealing its actual reasoning chops, or maybe its lack of them.
Okay, now here's where it gets really interesting. And honestly, a little bit weird, a bit perplexing. The study found that when these AI models were faced with problems that got progressively harder, they didn't just get a little bit worse each time. No, they went through 3 very distinct, almost dramatic phases. It reminded me a lot of being a student, tackling problems from easy peasy to, okay, I need to think about this, to, oh my gosh, this is impossible, that feeling. Some problems you just see the answer instantly. Others, you need to really focus, write things down, work through the steps, and then there are those problems that just feel completely overwhelming no matter how much you try. Well, it turns out AI experiences something uncannily similar. Let's start with phase 1, low complexity. This is where things were simple, like just 1 or 2 disks in Tower of Hanoi, or maybe swapping just 1 red and 1 blue checker. And here's the first surprise. For these really simple problems, the standard large language models, the ones without the explicit thinking process, the ones that don't generate that detailed chain of thought, they often performed better than the more complex large reasoning models, or at least just as well. And not only that, they were also more token efficient. What does token efficient mean? Well, basically, they use less computational power, less digital energy, less processing time to get the answer, which in the real world means lower running costs and faster responses. Think about it like this. If someone asks you what's 2 plus 2, you just know the answer is 4, right? Instantly. You don't need to mentally narrate, okay, first I take the number 2, then I conceptualize adding another 2, which results in the quantity 4. You just say 4. Writing down every single step for such a trivially easy task would actually slow you down and waste mental energy. And the study found something similar with AI. For these super simple tasks, generating a detailed chain of thought sometimes made the AI overthink. It could slow it down, or, even worse, cause it to make mistakes by overcomplicating something that should have been automatic. The paper actually calls this an overthinking phenomenon, even at this easy stage. It's like the AI is tripping over its own digital feet when it tries too hard on simple stuff.
Yeah, and if you connect that to the bigger picture, it's a really interesting insight into AI efficiency. It suggests that for basic, straightforward tasks, the whole machinery of generating detailed thoughts isn't just unnecessary, it can actually be counterproductive. It's kind of like asking a world-class chef to give you a detailed step-by-step explanation of how they tie their apron strings. For a simple, almost automatic task like that, an elaborate explanation is just pointless extra work. The AI, in these cases, seems to be doing the equivalent of an unnecessary internal monologue for something that should be almost reflexive, which maybe suggests a lack of metacognition.
Yeah.
Like it doesn't know when not to engage its complex thinking mode, it just defaults to it. Okay, so that's phase 1. Then we move into phase 2, medium complexity. And this is where the promise of those large reasoning models, the LRMs, really started to show. As the problems got moderately complex, we're talking maybe 3 to 7 disks in Tower of Hanoi, or adding more checkers or people in the other puzzles. That's exactly where the LRMs, with their chain of thought, showed a really significant advantage, a clear win. They were definitely more accurate at solving these problems compared to the stand of LLMs that didn't show their work. This stage feels much more like, say, tackling a harder math problem in school, maybe a multi-step word problem. You can't just guess the answer. You need to read it carefully, break it down, maybe write down the equations, do some calculations on the side. That systematic approach, writing down your steps, really helps you navigate the extra layers of logic and get to the right answer more reliably. And the study saw exactly that. The performance gap, as they called it, between the thinking models, LRMs, and the non-thinking models, LLMs, really widened here. The explicit steps, the ability to plan ahead, and maybe crucially, those attempts at self-correction we talked about, they really seem to help the LRMs handle these more intricate logical puzzles much more effectively. It showed that when the problem actually needs a sequence of steps, generating those steps helps.
Makes sense, right?
Yeah.
Yeah, that part makes intuitive sense. But then comes the really puzzling part. The part that's honestly a bit sobering when you think about AI capabilities. Phase 3. High complexity designs the collapse point. This is where the whole story just changes dramatically, and the limits of current AI become incredibly clear. Once the problems went beyond a certain point, a critical threshold of complexity, like trying to solve Tower of Hanoi with 8 or more disks, or maybe Block's World with around 40 blocks to rearrange something dramatic happened. Both types of AI models, the LRMs with their thinking and the standard LLMs, experienced a complete collapse. Their accuracy just plummeted, basically down to zero. It didn't seem to matter how much thinking the LRMs tried to do. They simply could not solve the problem anymore. They hit a wall. Just imagine for a second someone hands you an incredibly complex jigsaw puzzle, thousands of tiny pieces, maybe all the same color, or they ask you to solve some insanely difficult math theorem that needs years of specialized knowledge you just don't have. At some point, right, no matter how hard you try, no matter how many different approaches you attempt or how many notes you scribble down, you just can't do it. It's fundamentally beyond what you're currently capable of. The AI seems to hit exactly that kind of wall. It suggests that its current way of working just gets overwhelmed when the complexity, the number of possibilities, grows exponentially. Unlike maybe human intuition, which can sometimes find clever shortcuts or heuristics, or reframe a problem to make it simpler even when brute force fails, the AI just seems to drown in the sheer number of potential steps. And what was even stranger, and honestly quite baffling, was what happened with the LRMs at this collapse point. They actually reduced their reasoning effort. The researchers measured this by looking at how many thinking tokens they generated. You can think of tokens like words in their internal monologue or steps on their digital scratch pad. More tokens usually means more thinking, but here, even though these LRMs had plenty of token budget left, meaning they have the computational power and capacity to keep thinking for longer, this surprisingly seemed to, will give up, or at least scale back their effort significantly. It's almost like they didn't know how to generate useful next steps, so they just stopped trying as hard. It wasn't that they ran out of processing power. It seems they ran out of valid ideas for how to proceed. They just couldn't find a path forward in that huge search space.
That observation raises a really deep and important question, doesn't it? Why would these advanced AIs essentially give up or think less precisely when the problem gets exponentially harder? It strongly points towards a fundamental scaling limitation in how they reason. It's not just about needing more memory or faster processors. It seems to be a conceptual bottleneck. They reach a point where the inherent complexity of the problem itself just surpasses the ability of their current architecture to build a coherent step-by-step solution. It's like the map becomes too complex for their navigation system to handle. It's a conceptual roadblock, more than just a computational one. And think about how we humans sometimes react when we're totally, completely stuck on a problem that feels impossible. Sometimes, even if we technically have more time or energy, we just stop trying as hard, don't we? Or we kind of mentally disengage because the task feels so overwhelming, so hopeless. The sheer difficulty can lead to a kind of mental shutdown. The AI in this collapse phase seems to be showing a remarkably similar pattern, which suggests a fundamental boundary in its current reasoning architecture. This giving up is a fascinating crack in that illusion of thinking. It shows their process isn't necessarily intelligent in how it manages effort or recognizes when it's completely lost, especially when faced with truly novel, super complex challenges. It seems optimized for generating thought steps rather than strategically using thought to find a solution or even knowing when to stop trying.
Okay, so if these AIs are thinking by generating these chains of thought, what's actually going on inside? What do those thoughts look like as they wrestle with these puzzles? The researchers didn't just look at the final score, right or wrong. They went much deeper. They meticulously dissected the reasoning traces, literally every single step, every line of that internal monologue the AI produced. This gave them this incredible, almost microscopic view, a real magnifying glass into the AI's actual problem-solving process, step by step. And what they found brought them back to that overthinking idea we mentioned earlier, but with more fascinating detail. Remember, for the simpler problems, like just 1 to 3 disks in Tower of Hanoi, the really surprising thing was that the AI often found the correct solution quite early in its thought process. It would hit the right answer relatively quickly, but then it would just keep going. It would keep exploring and generating more steps, often generating incorrect solutions after it had already found the right one. It's like it couldn't recognize its own success and just stop. Imagine you're doing a crossword puzzle, right? And you figure out a word almost instantly. You know it fits. The letters match. The clue works. It's definitely correct. But then, for some bizarre reason, you carry on and write down 3 other completely wrong words in that same space just to explore options or double check, even though you already nailed it. That would be a total waste of your time, your pencil lead, your mental energy, wouldn't it? The study calls this overthinking, and it leads directly to a waste of compute. The AI is burning digital energy and time on totally unnecessary and often wrong pathways. The paper specifically noted this pattern. The distribution of incorrect solutions is shifted more upward towards the end of thinking compared to correct solutions, meaning the wrong answers tended to appear after the right ones had already been found. This overthinking really highlights a lack of efficient stopping criteria, maybe a lack of metacognition in the AI. It knows how to generate steps, but it doesn't seem to know when it has definitively solved the problem, or how to effectively prune pathways once a solution is found.
That's such a crucial insight. What's really striking there is that it's not just about finding the solution, it's about the efficiency of finding it, and critically, the ability to recognize when you found it. This suggests a pretty profound lack of true self-awareness in the AI's process, an inability to just stop generating possibilities once a correct path is clearly established. It's almost like it's programmed to produce a certain amount of thought, regardless of whether the problem's already cracked, which leads to this really weird inefficiency. It doesn't seem to have that clear aha or eureka moment that lets it confidently stop and say, okay, got it. Now, interestingly, as the problems became moderately more complex, the patterns observed inside the AI's thoughts actually flipped, which is fascinating in itself. Instead of finding the right answer early and then wandering off, the AI would typically start by exploring lots of incorrect solutions. It would stumble around, follow various dead ends, make what seem like numerous mistakes, but, and this is the important part, only later on, often quite deep into its lengthy thought process, would it finally land on the correct solution. This behavior is actually much more like how a human detective might solve a really complex mystery, isn't it? They might follow several wrong leads at first, maybe interview the wrong suspects, get sidetracked by red herrings. But eventually, after careful investigation, systematically ruling out the bad ideas, eliminating possibilities, and piecing together the clues, they finally find the crucial piece of evidence and connect the dots to the right answer. The source paper mentions this shift too. The distribution of incorrect solutions is shifted more downward compared to correct ones, meaning the right answers tended to appear later in the process for these medium problems. This does show some limited self-correction mechanism is working. The AI seems to be learning to prune some errors as it goes along, but it's still clearly a very inefficient, highly exploratory, almost brute force search through a huge space of possibilities.
Right. But then we get to those high complexity problems again, the ones where everything fell apart, the collapse mode. For these really tough, seemingly insurmountable challenges, the AI simply failed to generate any correct solutions at all, anywhere within its entire thought process. It just kept generating wrong ideas, maybe cycling through the same errors or exploring pathways that could never lead to a solution without ever landing on a single valid path. It's like it got completely lost inside its own thinking, tangled up in incorrect steps, and couldn't find its way out, no matter how many thinking tokens it used.
Yeah, that collapse is fundamentally different from just being inefficient. It really is like hitting a profound, absolute mental block, where no matter how much you think or how many steps you generate, you simply cannot find the solution path. The AI is genuinely stumped here, not just taking a long time. It suggests that beyond a certain threshold of complexity, the sheer number of possible wrong turns just completely overwhelms its ability to search for and identify the correct sequence. The combinatorial explosion, the rapid branching out of possibilities becomes just too vast, and its internal search methods, its heuristics, they just fall apart, leading to complete failure. It's as if its reasoning ability doesn't scale smoothly with the problem's difficulty. At some critical point, the complexity just breaks the mechanism.
So if we try and pull all these threads together, what's the big takeaway from dissecting the AI's thinking like this? It really reveals that these large reasoning models, even with their sophisticated ways of generating steps, have pretty limited self-correction capabilities. Yes, they can sometimes improve on their initial guesses and refine their approach on moderately complex problems, that's clear. But there are also these fundamental inefficiencies, like the overthinking on easy problems. And more importantly, there are clear hard limits to how much they can improve just by thinking more, especially when things get really complex. It's not just about giving them more time or more processing power. It seems to be about how they think and what the inherent flaws or limitations are in that process itself. The illusion, maybe, is that simply generating more thought automatically leads to better problem solving across the board. This research suggests that's not true. You normally think, if you give a computer a machine, literally built for precise execution, the exact step-by-step instructions for solving a problem, like a perfect recipe, you should just follow them flawlessly. Right? That's kind of what computers are for. But this deep dive uncovered some really surprising limitations that kind of challenge that basic assumption about AI. Specifically, for the Tower of Hanoi puzzle, the researchers tried something fascinating. They actually gave the AI the optimal mathematically proven step-by-step algorithm on exactly how to solve it. It was like handing it the perfect blueprint, an infallible instruction manual. You'd absolutely expect a machine to just execute those steps perfectly, logically, reliably, and achieve the best possible performance, right? But here's the truly astonishing finding. Even when they explicitly gave the AI this perfect algorithm, its performance did not get better. And the collapse point, the level of complexity where it completely stopped being able to solve the puzzle, happened at roughly the exact same complexity level. Now that is a really profound discovery, because it goes against our core intuition about how computers should work. We build it precisely because they're supposed to be amazing at following instructions with perfect fidelity. Yet here, even with a flawless recipe for solving the Tower of Hanoi, these advanced AIs still hit the same wall. Imagine giving someone a perfect, detailed recipe for a really complicated multi-layer cake. Every ingredient measured precisely, every instruction crystal clear. But they still struggle to bake it correctly once it gets beyond a certain level of complexity. It suggests the problem wasn't about the AI finding the solution or devising the strategy. It seems to be about its fundamental ability to execute a known, complex sequence of steps consistently and without error. And that's where they struggled.
That finding is absolutely fascinating, I agree, and it highlights a potentially very deep limitation. These AIs seem to struggle with what we might call exact computation, or following precise logical steps faithfully, even when they're explicitly told what those steps are. It raises really critical questions about their true symbolic manipulation capabilities. Symbolic manipulation is a core idea in AI, It's the ability to understand and operate on abstract symbols and rules, not just recognize statistical patterns. Think about learning algebra in school. You're not just memorizing specific answers like 2 plus 2, 4. You're learning to manipulate abstract symbols like X and Y and operators like plus and implies according to strict rules, rules that apply generally regardless of the specific numbers. That's symbolic manipulation, applying general rules to abstract concepts. If these AIs can't reliably execute a given algorithm for a complex task, it implies there might be a deeper issue in how they handle precise step-by-step logic. It suggests they might still be functioning more like incredibly sophisticated statistical pattern matchers rather than true rule followers in a deep, generalizable sense. They might recognize the patterns associated with the algorithm, but struggle with the actual mechanics of executing it perfectly over many steps. And there was another striking observation that points in a similar direction. The inconsistent reasoning across different puzzle types. Take the Claude 3.7 Sonnet thinking model, for example. It showed vastly different failure points depending on which puzzle it was trying to solve. In Tower of Hanoi, which inherently requires potentially hundreds or thousands of precise moves, it could actually make up to 100 correct moves for a pretty complex N10 puzzle before it failed. That's quite an impressive sequence of correct actions. However, for the river crossing puzzle, it could only produce valid solutions requiring up to 4 moves. Even for a relatively simple Endry version of the puzzle that only needed 11 total moves to solve optimally, it failed after just 4 steps. That's like having a student who's an absolute whiz at calculus, handling really complex equations, but then completely struggles with basic arithmetic word problems, even if those seem objectively much easier. Why the huge inconsistency? Well, the source paper offers a possible explanation. They suggest that complex river crossing puzzles, like N2, might actually be quite rare on the internet, the AI's training ground. So the AI might simply not have seen enough similar examples or patterns during its vast training phase to effectively memorize or learn the solution patterns for that specific type of puzzle logic. This implies its performance is still heavily influenced by the distribution of its training data, how much specific similar material it encountered. It's not necessarily demonstrating a truly generalized ability to apply reasoning principles equally well to any novel situation. This inconsistency isn't just a small quirk. It highlights a critical limitation. Even these reasoning models seem heavily reliant on their training data specifics. If a certain type of logical problem is underrepresented in that data, their supposed general reasoning doesn't just magically compensate. It suggests that achieving true generalizable intelligence, the kind humans have, allowing us to adapt and tackle genuinely new problems we've never seen before, remains a major hurdle for AI. It seems less like a universal reasoning engine and more like an extremely advanced but still context-dependent pattern recognition machine.
Yeah, that really drives the point home, doesn't it? That even with these impressive thinking abilities, these chains of thought, these advanced AIs aren't uniformly good at all kinds of problems. Their success seems really tied to how much similar stuff they've seen before and how well the patterns they learned happen to map onto a new challenge. Which again brings us right back to that fundamental question. Are we witnessing true flexible reasoning here? Or is it an incredibly sophisticated, highly advanced form of pattern matching and recall that just creates this compelling illusion of thinking? So, okay, let's try and wrap this up. Pulling all these threads together, what does this Apple research, this deep dive, really mean for all of us? For people trying to understand AI, maybe use AI, or even build AI. We've seen pretty clearly that large reasoning models, while they are incredibly powerful and definitely can break down problems into steps, they aren't perfect general problem solvers. Not by a long shot, it seems. They genuinely shine on tasks of medium complexity. That's where their explicit thinking process, the chain of thought, really does give them a significant edge. But they also demonstrably struggle and even seem to just give up when problems become truly complex. They hit this kind of conceptual ceiling, a point beyond which they simply can't progress reliably, even if you give them the answer key or more thinking time. This deep dive really shows us, I think, that AI's thinking is still very much a work in progress. The conversation shouldn't just be about whether AI is smart or not. It's much more nuanced. It's about how it's smart, what the actual mechanisms are behind that intelligence, and crucially, where its current fundamental limits lie. And understanding these nuances, these limitations, is absolutely vital for everyone. It helps us figure out where to deploy AI effectively, making the most of its strengths. But just as importantly, it tells us where we still absolutely need human brilliance, human intuition, and that amazing human knack for flexible, generalizable problem solving. It's about being informed users, thoughtful developers, and realistic observers of this incredible but still evolving technology.
Yeah, and this study, in a way, it really challenges our basic intuitions about intelligence, doesn't it? Both human and artificial. It leaves us with a really important question, something for you, the listener, to think about. If giving an AI the exact perfect algorithm doesn't actually help it solve truly complex problems, and if it struggles so much with novel puzzles that it hasn't effectively memorized patterns for, then what does it actually take? What will it take to build an AI that can genuinely reason in a flexible way? An AI that can adapt to any new challenge, truly like a human can. Think about your own learning experiences. When you learn something genuinely new, you don't just memorize steps or facts in isolation, do you? You connect ideas, you build mental models, you adapt your understanding when you encounter something unexpected, and you can often figure out solutions to problems you've never seen before by applying broader principles. That seems to be the fundamental challenge for AI right now, reaching that level of flexible, adaptable, generalizable understanding. So, what breakthroughs do you think would be needed? What needs to change for an AI to move beyond this potential illusion of thinking and learn to think with genuine, adaptable intelligence? Keep exploring, keep asking those big questions, because the future of AI is absolutely still being written, and our informed understanding, your understanding, really does play a role in shaping where it goes next.